Hey, welcome back to the shop. This is the second part on the cross-slide modification. And you just saw me machining this piece here. Just a piece of free cutting mild steel, drilled and tapped with 6mm thread on one side. And this is going to be the extending piece for the cross-slide feed screw. And as you can see, I have the cross-slide feed taken out of the lathe, and I still had to work on the lathe, doing facing operations and parting off and stuff like that. And without the feed screw, yeah, it doesn't work. I had to tilt the compound slide to 90 degrees, and that way I was able to do the machining operations by manipulating the bed slide and using the compound slide as a cross feed. Really not the best way to do it, but I only have one lathe, so yeah, have to do it some way. And this extending piece will screw onto the existing screw here. There will be a set screw in this piece, Loctited in with Loctite 648 high strength Loctite, and the second piece will just be screwed on, also with Loctite, tightened down, wait until it's hardened, and then it will be machined as one piece. We will chuck up the whole feed screw in the lathe and machine this end. So first of all, we join these pieces with some Loctite together. Okay, we're cleaning the bore with a Q-tip and some alcohol. To give the Loctite a fighting chance. Same for the bore and the extender piece. As I used some cutting oil, I want to have it at least somewhat clean. But Loctite is pretty tolerant to dirt in threads for some reason. Okay, Loctite 648, high strength retaining compound. And yes, I buy the big bottles, I get them empty pretty fast. I use that stuff a lot. So get the, yeah, where a little helps, a lot can't hurt. So that's, excess will be squeezed out. So screw it in. I'm not going to bottom it out. Some of the excess off, and now we wait until it has kind of set. Yes, I'm going to leave you watching Loctite dry. Okay, just joking. Of course I would never let you sit here 20 minutes watching Loctite dry. It's tight enough so we can screw it into the other piece. Get some Loctite in there. Screw it in and tighten it down with the proper torque of about some Newton meters. Good. I used this technique with the set screw as a connector piece a few times, and it always worked out very well. Okay, we're back at the lathe, and I checked the spindle up in the 3-char check, and I was just checking for runout. And of course on the existing surfaces on the spindle, and there is not much runout. It's in fact pretty much 1/100th of a millimeter. Yep, perfect. Now we can very carefully face off the end, center drill it and support it with a live center. Very careful because it's pretty wide hanging out the end, and you see that my extension wobbles a bit, but that's no problem because we're going to machine it anyway. So let it wobble. Yeah. Let's face it. To do the facing, I'm using a very sharp, high-speed tool because I can't risk to put very much cutting force into this. Okay, that's enough of a face. Now we can take a small cent to drill. Okay, now we can turn this this extended piece down to the desired dimensions. On the measurement, and we're 3/100th of a millimeter heavy, so let's take an old friend. That's a lathe file, and the difference to a normal bench file is it's single cut and it's at 45 degrees, so it ejects the chips very nicely. They don't leave the best finish, but they cut pretty fast. And as we're just threading this diameter, doesn't matter as much, and we are at 12.00. Next we need to cut a step down to 10 millimeters where the actual dial will run on. Okay, I turned the 10 millimeter step and I test fitted the parts. This is the bearing block. I already pressed in the 2 bearings. It slips on like here. We still have to thread this area here with the fine thread so we can adjust our bearings. But for the test this doesn't matter, and we have our 2B dial, and she fits very nicely on there. A little bit of play, and when you move it all the way up to the shoulder, the bearing block and dial don't touch each other, and that's what we wanted. We want the dial not to rub on the bearing block or the vernier ring here. So yeah, that's pretty good. Okay, I did the threading off camera and got the fit quite nice. As you can see, this is just a regular 12x1 fine thread knot that I'm using to test it. And now we can assemble it with the bearing block with bearings in it, and we have a spacer ring. This is a hardened and ground distance bushing. I have no idea where this is from. Found it in my scrap box. This goes on, and there's the nut. I can adjust the axial play of the bearings, and I want them to be slightly preloaded, so they are without any play. That's preload. And this is not the final nut I'm going to use. I will make a nice nut that can be locked with a set screw. This is just for testing. And then we have our dial, which slides on like this, and it's free to turn because it has no means of locking until now. And next step will be to drill. What will be the next step? We have to drill it from the front for the locking mechanism of the dial. Okay, and power tapping 5mm. Time for a joke about balls. Or, no, let's don't go there. We need a 4mm ball bearing ball, and I have one. Every time I throw up an old bearing, I take it apart and salvage the balls. Can't throw something such nice out. Somebody went into great extent and made these very precise and hardened and ground and to very high specs, so you can't throw something like this away. Okay, I just wanted to show you how this clamping mechanism for the dial works. We have the spindle, and I cross-drilled and reamed it to take this 4mm ball bearing, or bearing ball, whatever you want to call it. And this little bugger keeps rolling away. I have a gob of weasel snot here. That's Tom Lipton's weasel snot. It's nice for holding small parts so they don't roll off your table. And the end of the spindle is drilled through into the cross hole with a 4mm drill, and the end, about 50mm deep, is tapped with a 5mm thread for this thumb screw. This is not the final thumb screw we're using, this is just cobbled together so I have something tested. And how this all goes together is pretty simple. We take our dowel pin, this goes in. When we push it down, and we look in the cross hole, we can see that the pin eventually reaches into the cross hole right now. And we push it slightly back, not all the way, only a bit. And we take our 4mm ball bearing ball and drop it into the 4mm cross hole. Goes in quite snug, so it doesn't fall out by itself. And now, when we push in from the end, the bearing ball comes out. Don't know if you saw this. I can push it back into the... I should be able to push it back. The dowel pin has a chamfer on the end, and that pushes out the bearing ball. I think you saw it this time pretty good. Of course, it doesn't have to go out that far because there is the bore of the dial over the cross hole. And it works like this. We take the dial, push it over here. This slips on up to the shoulder, and when we take our thumb screw and turn this in, right now it's free to spin. And when we tighten this set screw slightly, it pushes in the dowel pin, and the dowel pin pushes out the ball, the bearing ball, in the cross hole. And this locks the dial. And when we loosen the thumb screw, we can freely spin and adjust our dial, and we can lock it back. So that's the locking mechanism for the dial, and I'm very happy how well this works. With just an eighth of a turn, we can go from completely free spinning to locked safely in place, and this feels so much better than the stupid friction lock on the dials, or the some manufacturers have a big knurled nut that presses against the dial. That's okay, but when you tighten the nut, the dial tends to move, and with this setup there is absolutely no movement in the dial when you tighten it. So I think that's a superior method. And only to be sure, I didn't come up with that. I saw this in the book from George H. Thomas, and with the only difference that he doesn't use a ball, he uses a cross pin that has a 45-degree flat on it. But I have not enough room in here for a cross pin, so I used the ball. And as the ball and the dowel pin are hardened, it shouldn't wear much at all. And yeah, you see, spins, locks. I could play with this the whole day, but I have other things to do. Okay, and this is how the new bearing block with the dial and the dial lock look mounted on the lathe. And when we loosen the set screw or the thumb screw, we can freely rotate the dial. Let's make some lines on there so you can see it. And there's our 0, so we can turn our dial where we need it and lock it. And of course I don't have a hand crank on there right now, but yeah, you see the concept. And when I turn this really feels very nice and very subtle. And there is really very little backlash. Doesn't feel like there is in the bearing block any backlash. The only backlash that you maybe can hear, that's in the spindle nut. But apart from that, I'm very happy. This is the ring with the vernier. That's also free to rotate, and this will just be locked with a a radial thumb screw from below, so you can slightly adjust it if you need. And also it feels like the stick slip effect when you try to advance your the axis of your machine by a very little amount, like 1 or 2 hundredths of a millimeter, and at first nothing happens, and then the slide jumps because it overcomes the friction. It feels like this has reduced very much. It feels very, very precise, and I'm very happy, as you can tell maybe by my reaction. And yeah, that's it for this episode. Thank you for watching. See you next time.